Okay, so we're back now with our third in detail video, and we're actually looking at conservation of momentum tonight. So let's go ahead and let's take a little bit of look on conservation of momentum. Again, I'm going to kind of go big picture here. Big picture says that an object has momentum and another object has momentum, and the sum of the momentum in the system before a collision will be equal to the sum of the momentum that we have after the collision. Okay, so again, momentum is going to be conserved. A lot like how we conserved energy. Okay, the energy that we had before is going to be equal to the energy that we have after. Momentum that we have before is equal to the momentum that we have after. So that's our big core picture here. All right, and so again, statement is total momentum of all objects interacting with one another remains constant regardless of the nature of the forces between the objects. Okay. I did find a couple of good videos that I'd recommend going and watch. One is actually an astronaut who's in space, and he's actually explaining the conservation of momentum with tennis balls. The cool thing about it is that the tennis balls are floating because they're weightless essentially because you have no gravity impacting them. And so he's actually able to show conservation of momentum with tennis balls. The other one was just a little animation I'm guessing somebody created for a probably a computer animation class or something. It was about a minute-long animation showing a cannon being fired and how the cannonball comes out with a certain amount of momentum, and then the recoil of the cannon is going to have equal and opposite momentum. Okay, very much like the example that I'm talking about right here. Okay, so here's our cannon. You can see our cannon. It's before the system, nothing's moving. So in other words, we have no momentum at this point in time. All of a sudden, inside of the cannon barrel here, okay, there's the cannonball sitting inside there. There's the explosion. Boom. Okay, fires the cannonball out of there. Okay, the moment that happens, we actually are imparting momentum on the cannonball, but we're also putting momentum on the cannon itself. Okay, and so in other words, the amount of momentum that we have in the system is going to remain the same. So the amount of momentum that we had before was 0. The amount of momentum that we're going to have after is 0, which means that the momentum of the cannon is going to be equal to the momentum of the ball, but in the opposite direction. So if I consider this to be the positive direction, this would be negative. So in other words, the sum of the momentum is still going to be equal to 0. So the amount of momentum that I have before is going to be equal to the amount of momentum that I have after. Typically what we do when we try to solve this is we say that the momentums are going to be equal. I like to drop the negative sign just because I want to look at the two values being the same, understanding though from my picture that one is in the opposite direction as the other. Because again, it's about the fact that the two momentums, the sum of the momentums is equal to 0. So in other words, the sum of, let's get a little better on here. The sum of my momentums is equal to 0, which means that the momentum of the ball plus the momentum of the cannon have to be equal to 0. So that's why I apply that negative, because it's in the opposite direction. Okay, so that'll be equal to 0. So in other words, when I go through and I do the problem, I like to just say the momentum of the cannon is equal to the momentum of the ball. Okay, so we know maybe the mass of the cannon, we know the mass of the ball, and then maybe we know one of two velocities. Okay, now let's look at an example problem on one of these. So here we have conservation of momentum problem. I'm going to do two examples tonight. So we have a 76 kilogram boater initially at rest in a stationary 45 kilogram boat, steps out of the boat onto the dock. If the boater moves out of the boat with a velocity of 2.5 meters per second to the right, what is the final angular or final velocity of the boat? So in other words, here's my dock. Okay. Here's my boat. And here's my person stepping out of my boat. Okay. And when they step out with their velocity, 2.5 meters per second, and their mass, the boat wants to go this way, okay, and it has a mass of 45 kilograms. So in other words, we're looking at a situation where, and maybe you've experienced this, where the boat wants to go this way and you want to go this way, and sometimes what happens is you end up falling in the water. I don't know. I've never had that happen before. All right. So again, my momentum of the boat is going to be equal to the momentum of the boater. Okay? So again, it's the mass times the velocity is equal to a mass times the velocity. You have to remember, though, that these have to be of the boater and these have to be of the boat. Okay? So in other words, the mass of the boat, 45 kilograms. Velocity of the boat, unknown. Mass of the boater, 76 kilograms. Velocity of the boater, 2.5 meters per second. So now we're just going to solve for V. So our velocity becomes, let's turn my calculator on, 76 times 2.5 divided by 45, 4.2 meters per second. Okay, and you should be able to notice this velocity is bigger than my velocity here. But the reason why is because I have more mass than my canoe, apparently. I'm guessing. It's got to be a Kevlar canoe if it weighs that little compared to maybe a heavy aluminum boat. I don't know. Anyways, so that's how we go ahead and we solve that type of a problem. All right. Now let's look at, we have a boy on a skateboard and it's initially at rest, tosses a jug of water in the forward direction. The jug has a speed of that relative to the ground, so that means that the skateboard moves in the opposite direction. Okay, so I'm going to draw my little picture here. Here's my skateboarder. Okay, here's the jug of water. We're going to push the water this direction. Velocity 3.0 meters per second, and it's an 8 kilogram jug. We find that the boy on the skateboard goes this direction, 0.6 meters per second. And what are we looking for? Find the boy's mass. Mass unknown. Now, it's the mass of the boy that's unknown, not the mass of the skateboard, because they did tell us the mass of the skateboard. So what I'm going to do is I'm going to treat this just like the last problem. Only I'm going to solve for a mass instead of solving for a velocity. And then what I'm going to do is after I get that mass, I'm going to subtract the mass of the skateboard. Okay? So again, I'm just going to set this up where I look at it and I say, okay, my momentum of the skater is equal to the momentum of the jug. Okay? And so again, the mass times the velocity is equal to a mass times a velocity, but remember that these have to be for these items. Mass of my skater, I don't know. Velocity, I do know. Mass of my jug, I know. Velocity of the jug, I know. So then I'm just going to divide by 0.6. My mass comes out to be 8 times 3 divided by 0.6, 40. Okay, this would be kilograms, but that's not the mass of the actual boy. That's the mass of the boy plus the skateboard. So I have to subtract from that 2 kilograms. So it's a 38 kilogram boy. Okay, So there you go. It's momentum problems, and it's the big thing is you just have to remember the amount of momentum that I have before in the system is going to be equal to the amount of momentum that I have after the system. And so we can kind of look at it from that standpoint. Again, we've got a number of problems that we're going to work on. I do suggest watching the 2 videos that I did post, and I think I posted a reading as well. So, all right. Questions in class tomorrow.